In this video, we're going to do the last little bit about the pre-measure and its Carathéodory extension. Namely, we want to consider when this Carathéodory extension is the unique extension of our pre-measure. So on your assignment, you will see there's a question about giving a pre-measure on some algebra. There can be some other measure that extend this pre-measure, but it's different from the Carathéodory extension. So in this proposition, we're going to show that if your Carathéodory extension is actually sigma finite, then your extension is the unique extension of your pre-measure. So in other words, if you have another measure on the same sigma algebra where it extends your pre-measure, so when you restrict this mu on your original algebra, you get the pre-measure mu back, then this new measure has to be the same as the Carathéodory extension mu bar. All right, let's try to prove this fact. The first step, we want to compare nu of a set with mu bar of E. So suppose I have some E, which is inside the sigma algebra B, which contains all the mu star measurable sets. Then let's consider on one hand, this mu bar of E by definition is no other than the outer measure of E coming from the pre-measure, so is basically the infimum of all the summation of these mu of an and greater than or equal to 1, where each of these an come from the algebra, and an is a cover of E, so E is contained in these ANs, all right? So this is just the definition of the outer measure mu star, and that's exactly how we define the Carathéodory extension mu bar. All right, so from there, so let's suppose I have such a cover of E, so suppose AN is in A, so that E is contained in this union, and greater than or equal to 1 of these AN. Then let's think about what happens to this nu of E. Well, nu we know is a measure, so it's certainly monotone. So it will be less than or equal to nu of this union and greater than or equal to 1 of each of these an. And because we know measures are also satisfy this sigma subactivity, so this is less than or equal to the sum and greater than or equal to 1 of mu, sorry, not mu yet, is still mu of each of these an. Well, now these an are coming from A, so each an is from A, and we know that when you look at an element from this algebra A, the nu extends the pre-measure mu. So mu restrict to A is simply mu. So each of these nu of an is no other than mu of an. All right, so they are the same. So when I take the summation, they are still the same. All right, so now you see that this nu of E, okay, so let's see what we proved. The nu of E on the left is less than or equals to each of the sum, where you have some an that's covering this E. And if you notice, the mu bar of E, or the outer measure of E, is simply the infimum of the right-hand side. So let's take the infimum on the right. So take infimum. So we will have mu of E, because it's less than or equal to all of them, is certainly less than or equal to its infimum, which is the mu star of E, or you can say just mu bar of E, because E is taken from the mu star measurable set. All right, so that's the first step. Well, it proves one side of the inequality. So we want to prove the other side. So let's prove a little short lemma. Okay, so I want to show the following. Suppose I have some an that's contained in A. All right. Then I want to show that the nu of their union, and going from 1 to infinity of these an, that's equals to the mu bar of their union. Okay, so the mu and this mu bar will agree on countable unions of elements from the algebra. Okay, that's what I'm going to claim. So the proof of this fact is fairly simple. If you follow Ken Davidson's course note, you'll see you can do the standard trick of breaking these AN into disjoint union, and then you can go from there. Okay, there's actually a little bit simpler way of going around this. So you know this countable union of AN, because mu here is a measure, we know is continuous from below, so is actually equals to the limit of these mu of the first finite union from n from 1 to this big N. Okay, so here as you add in union more and more AN, you're having more and more, so you're getting an increasing chain of sets, and their limit is this big union, and you can see that because mu is continuous along this chain, well, you have this limit. But now each of these finite union is actually contained in the algebra, so we know on this algebra, the mu and mu bar, they all agree with your original pre-measure. So this is no other than the limit when n goes to infinity of, you can say, mu of them, because this mu will extend the mu, this pre-measure mu. But on the other hand, it's actually also equals to the mu bar, because we saw mu bar extend this mu from last video, so that you can replace these by mu bar, and they give you the same limit. And now mu bar itself is a measure, so on the right hand side you have this limit will equals to this mu bar of their union again by a measure is continuous along these increasing chain. Okay, so this proved the second fact we have. All right, now let's try to prove that mu bar and nu are actually the same. Okay, so let's first look at a set that has finite measure. So suppose I have E contained in this B, where this mu bar of E is less than infinity. So I have some finite set first. All right, so how can we approximate this? Well, remember, we only know mu bar and nu will agree on the algebra A, so we have to try to put everything back to the algebra. Okay, so by definition, again, there exists some cover using this algebra, so we have an and going from 1 to infinity from the algebra, so that E is contained in its cover, so n greater than or equal to 1 of these an, and I want this cover to be a good approximation of mu bar. So mu bar being the infimum, so mu bar will less than equals to the summation of each of these mu of an and greater than or equal to 1. Well, I want to make it a good one, so let's make it less than equals to mu bar of E plus epsilon. Okay, so I probably should have, say, let's pick every epsilon greater than 0 first, and then we pick a good approximation of these an. Let's let A to be the union of these an. Okay, so n greater than or equal to 1. Well, we know that E is contained in A. And because this an is already a good approximation of mu bar of E, then first of all, let's show that A is actually also a pretty good approximation of E. Okay, so why is that? So let's consider the following. So if I consider what happens to mu bar of A, okay, well, the mu bar of A, you can break it into two parts. One is mu bar of E, which is a subset of A. So because it's a subset, the rest is just A take away E. Okay, so here A, again, A should be in your sigma algebra because each AN is in the algebra. So now I have break it into these two parts, and let's see what we have. We have that the mu bar of A, which by definition, this A is no other than the countable union of these AN. So they are less than equals to the summation of each mu of AN. Okay, so n greater than equal to 1. Okay, this is just by the sigma subadditivity. So now let's remind you how we picked these ANs. Well, it's a good approximation of mu bar of E. So based on this inequality, we have this summation is less than or equal to mu bar of E plus an epsilon, where the epsilon is fixed. All right, so now mu bar of E is finite, so I can cancel them out because I'm canceling out a finite number. It doesn't work when mu bar of E is infinite. So this allows us to say, well, now I have mu bar of A take away E is actually less than epsilon. Okay, so I can probably, let's just say less than equal to epsilon for now. All right. Okay, so basically it shows that A itself is a good approximation of E as well. Okay. So now let's try to look at what happens to nu of E. Okay, so let's look at nu of E. All right. So, well, the nu of E, we know nu is a measure, so I can break it. I can consider nu of A, which contains E. So I can just minus whatever is left. So A take away E. That's going to be equal, okay, because nu is a measure here. And we just proved that because A is a union of elements from the algebra, so let me remind you, A is just this countable union. And in number 2, we proved that when you have a set that comes from a countable union of the algebra, the mu bar and mu will agree. So this first one should be equals to mu bar of A. Okay, they're the same. Okay, so now let's look at the second one. Okay, so what's my goal here? I want to show that this nu of E is actually greater than equal to, this is what I want to show. I want to show this is greater than equals to mu bar of A, maybe minus an epsilon, okay? So this is what I want. So in other words, I need to give an upper bound of mu of A take away E, okay? So what's an upper bound of mu A take away E? Well, in the first step, we actually showed that this is less than equals to mu bar of A take away E, okay? The mu bar will always give you some bigger number, okay? This is by 1, and I should probably say this is by the item 2 we did before, all right? So by mu bar of E, we just proved that is less than epsilon, so this is less than equal to epsilon. So we have an upper bound of this mu of A take away E is at most epsilon. So when I want to minus this mu of A take away E, I at most reduce it by epsilon. So everything should be greater than equals to this mu bar of A minus epsilon. So this is no longer what we want to show. We can actually show that. Okay, so just because of this upper bound of the nu, we have the desired inequality. All right. So this proves that the nu of E will be greater than or equals to mu bar of A minus an epsilon. Okay. Well, then what do we want? We want to compare nu of E with mu bar of E. Well, now we have mu bar of A, but A and E are really close, and actually A contains E, right? So we have this nu of E, we just showed is greater than or equal to mu bar of A minus epsilon. Let me copy it here. And because A is greater than E, or it contains E, so mu being a measure is monotone, so it's greater than or equal to mu bar of E minus epsilon. Okay, so this is just by that. And because epsilon now is arbitrary, so we have this nu of E is also equals to mu bar of E. Okay, so actually have greater than equal to, but we showed the less than equal to from 1, so we can conclude this is equality. Okay, so this is, they all agree on sets with finite measure. Okay, this is by item number 1. All right, so finally, I need to consider what happens when I have something that doesn't have a finite measure. Well, so that's the last step. So let's take any E coming from this algebra? Well, because the entire measure mu bar is sigma finite, so mu bar is sigma finite, it means I can find increasing chain of finite measurable sets that's just union up to the entire thing, okay? So there exists, let's say, maybe let's call it Bn inside B, where I have an increasing chain B1 containing B2 and so on. And each of these mu bar of Bi is going to be less than infinity, and their union of these Bn is the entire set. Let's call it X, okay? So now, because each of these Bn is finite measure, then I can just consider En, which is the intersection of E with each of these Bn, okay? So, well, it should have finite measure as well, so mu bar of En will be equal to the nu of En because it has finite measure, okay? This is because mu bar of En is less than infinity. It's bounded above by mu bar of Bn, which is less than infinity. Now, if I want to now compare the mu bar of E, okay? Well, mu bar of E is no other than the union of these En n greater than or equal to 1. And these, because Bn are increasing, these Ens are also increasing, okay? You're intersecting with an increasing chain of sets. So now we have, again, by the continuity, we have this mu bar of this union is no other than the limit of these En, okay? I take limit when n goes to infinity. And because of each of these En, I have mu bar and mu are the same, so I have mu of En. And again, mu is a measure as well, is continuous along this chain. So I have is equals to nu of the union En, which is just simply nu of E, okay? So this proves our desired result. Basically, we showed nu and mu bar, they are the same thing. All right, just want to do a quick remark. So here is a quick remark about what we just proved. In fact, if we consider some sigma algebra C that contains the algebra A, but contained in all the mu star measurable sets B, then in fact, you will have an extension of this pre-measure mu, namely restrict your Carathéodory extension to the C. And you can follow the same procedure, and you can see that this is actually the unique extension of your pre-measure on the sigma algebra C. So what happens in reality is oftentimes you will find yourself where this B, this bigger one, consists of the Lebesgue measurable sets, which sometimes is a little bit too big, but you actually only need a unique extension on the smaller one, so most of the time you only need it on the Brown measurable sets. So the same procedure still applies. You still have a unique extension on these Brown sets. Basically, you just take the Lebesgue measurable sets and you restrict yourself to the Brown measurable sets, and you will get the unique extension.